Good day, the topic is total pressure on an inclined plane surface. Taking the second case, for an inclined plane, let us consider three methods of solution for the determination of force and location. First is the pressure diagram method. So for the process, first, identify points at top and bottom of the submerged plane. For this sample, we will consider points A and B. Next is to determine the pressure at the pre-identified points. For homogeneous fluid or single fluid, use P equal to gamma times H. For layers of fluids, consider P equal to P sub A plus the summation of P sub Li. Better to present solution in table form. And identify the points, depth H, and finally pressure P. For points, we have A and B. For H, it is the depth measured from free liquid surface for layers of fluids. The column for H is not needed. Again, for this column, it is only for homogeneous fluid or single fluid. So at A, since it is at free liquid surface, H is equal to 0. And at B, H is equal to H sub V. And next, for P at point A, since H is equal to 0, P is 0. And at point B, P is equal to gamma times H sub V. Assign pressure values, so 0 at A and gamma times H sub V at B. So draw the pressure diagram. So for pressure, it is uniformly increasing as the depth increases. And using this diagram, we can already estimate the value of the total pressure F, where F is equal to the volume of the pressure diagram. So that is the area of the pressure diagram, or A sub T, multiplied to the width of the submerged plane surface, which is represented with L or B. So for the sample diagram, F is equal to 1/2 times gamma times H sub V, which is the base of the triangle, times the height, which is H. Then multiply to the length or the width of the sample surface, which is B. But assign the distance from free liquid surface to the center of gravity, or CG, as H bar. And for this sample, H bar is equal to H sub V over 2. Then the actual area of the surface, that is H times B. Thus, simplifying the equation, we have F is equal to gamma times H bar times A. And for the location of F at the center of pressure, or CP, that is the distance y sub P, or centroid of the pressure diagram. For this sample, if measured until free liquid surface, it is 2/3 of H sub V. But if it is from the bottom, then consider 1/3 of H sub V. And for pressure diagram that is not a triangular prism, consider the concept of the moment area method, or Varignon's theorem. That is, A sub T multiplied with Y sub C is equal to the sum of A sub I times Y sub I, the moment area of the individual shape. And this is with respect to a common reference line. And for the process, divide the diagram to triangular shapes. So before we proceed, we have some notes. First, the pressure and force are always perpendicular to the submerged surface. Second, you can use the identified equation for F and Y sub P if it satisfies the following equation or criteria. First, only one fluid. Second, partially or submerged surface just at free liquid surface. Third, rectangular surface. And for the last note, if the criteria or one criteria are not satisfied, Then consider the process of pressure diagram. So this is for the first method. Next, for method number 2, which is the direct method, it is an ideal method because it is flexible and easy to use for any shape of the surface. First is for the total pressure F. For homogeneous fluid or single fluid, use F as equal to gamma times H bar times A. And for layers of fluids, which is applicable only if the surface is exposed to only one fluid, and if not, then use the pressure diagram method. Then for these layers of fluids, use F equal to P bar times A, where P bar is the sum of pressures of fluids at the center of gravity of the submerged surface, which is P bar equal to P plus the sum of P sub Li. So for the location Y sub P is equal to H bar plus E sub V. So for E sub V, consider the triangle for components. So the sine of theta is equal to E sub V all over E. And rearrange, we have E sub V is equal to E times sine of theta. For eccentricity E is equal to I all over A sub Y bar. And what is this Y sub Y bar? So for Y bar rather, so it is the equivalent value of H bar that is parallel to the inclined surface. So we will consider therefore the triangle for the components. So for sine of theta, it is equal to the opposite, that is H bar over the hypotenuse, which is Y bar. Rearrange, we have Y bar equal to H bar all over sine of theta. Then substitute everything to determine the value of Y sub P. And for the last method, we have method number 3, the components method. So let us determine the horizontal and vertical components of the resultant force F. So for the horizontal component, F sub H, consider the projected vertical two-dimensional surface and apply the concept of vertical plane surfaces. So for homogeneous fluid or single fluid, use F sub H as equal to gamma times H bar times A. While for layers of fluid, use F sub H equal to P bar times A. Again, P bar is the sum of pressures up to the center of gravity. So for the location, we have YP as equal to H bar plus E, where E is equal to I all over A times H bar of the projected surface. So for the vertical component, F sub V associated as the weight of the fluid above the surface. Then, F sub V, which is equal to the weight W, is equal to gamma times the volume. So for the resultant force, if we already identified F sub H and F sub V, then we will consider the force triangle and apply the Pythagorean theorem, that is for F, it is equal to the root of the sum of the squares of FH and FV. Okay, so let's take our first sample problem. So for problem number 1, a 30 meters long dam retains 9 meters of water at its 60 degrees inclined side. So determine the total resultant force acting on the dam and the location vertically measured from the bottom. So for method number 1, which is the pressure diagram, so assign points A and B at the top and the bottom of the submerged surface or submerged portion of the dam. Again, consider only the submerged portion of the dam. For homogeneous fluid, P is equal to gamma times height. Presenting in table form, identifying points H and pressure P. For points, we have A and B. And for H, that is measured from free liquid surface, at A, H is 0, and at B, H is 9 meters. Therefore, P at A is 0 since H is 0. And for point B, it is equal to the gamma, that is 9.81, times H, that is 9. Therefore, P is 88.29 kilonewtons per square meter. Assign the pressure values at A and B. Then, draw the pressure diagram. Next is to complete the details. Determine the value of the slant height H. For this triangle, so the sine of the angle 60 degrees is equal to the opposite 9 meters over the hypotenuse side, which is the unknown H. Rearrange and identify H as 10.392 meters. So updating now. So determine the value of force F. For F, it is equal to the volume of pressure diagram, or A sub T, the area of the pressure diagram, times L, the width of the submerged surface. Substitute values. Therefore, F is equal to the area of the triangle, that is 1/2 over the base, 88.29, times the height, which is H, the 10.392 meters. And with this area, multiply with the width of the surface, which is 30 meters, the length of the dam. F therefore is equal to 13,763.049 kilonewtons, so which is perpendicular towards the submerged surface of the dam. For the location of F from the bottom of the dam, represented with Y is equal to 1/3 of H sub V. Substitute H sub V, or the height of water, as 9 meters. Therefore, Y is equal to 3 meters from the bottom of the dam. So for method number 2, so determine the value of F for homogeneous fluid. That is, F is equal to gamma times H bar times A. And substitute values, we have gamma of water, that is 9.81 kilonewtons per cubic meter, times H bar, which is 4.5 meters. Then multiply to the area of the surface, or the actual area, that is 30 meters, times 10.392 meters. For F is equal to 13,763.049 kilonewtons, perpendicular towards the surface of the dam. So for the location F from the bottom of the dam, represented with Y, so from the figure, Y is equal to 4.5 meters minus E sub V. For EV is equal to E sine of theta. Determine eccentricity E, that is equal to I all over A times Y bar. And I for rectangular surface is 1 all over 12 times B times H raised to 3. For Y bar, associated with H bar, thus Y bar is equal to H bar all over sine of theta. Substitute H bar, that is 4.5 meters, and theta as 60 degrees. Therefore, Y bar is 5.196 meters. Substitute in equation of E. The value of E, therefore, is 1.732, and in equation of EV, as for theta, that is 60 degrees. EV is equal to 1.5 meters. And for Y, we have 4.5 meters minus 1.5 meters, the EV value. Therefore, Y is equal to 3 meters above the bottom of the dam. So last is for method number 3, which is the components method. So determine first the horizontal component. For homogeneous fluid, use FH equal to the gamma times H bar times A of the projected surface. Substitute the values. We have gamma of water, that is 9.81 kilonewtons per cubic meter, multiply with h bar, that is 4.5 meters, then multiply with the area of the projected surface, which is base 30 meters, times height 9 meters. The horizontal force component is 11,919.15 kilonewtons. Next, for the vertical component, F sub V is the weight of the fluid above. That is gamma times the volume. Fb therefore is equal to the gamma of water, that is 9.81 kilonewtons per cubic meter, multiplied with the area of the triangle using scissors hand formula or equation. That is 1/2 times the sine of angle in between the identified legs, which is 30 degrees, multiply to the product of the identified legs, that is 9 meters and 10.392 meters. So multiply to the product of multiply with the length of the dam rather, that is 30 meters. Thus, F sub V is equal to 6,881.524 kilonewtons. So for the resultant F, consider the force triangle and apply Pythagorean theorem. Therefore, F is equal to 13,763.049 kilonewtons. Again, this is perpendicular towards the submerged surface of the dam. And for the location above the bottom of the dam, y is equal to 4.5 meters minus e. Solve eccentricity of the projected surface. E is equal to I all over A times h bar. And for rectangular surface, I is equal to 1 all over 12 times B times h raised to 3. Substitute B as 30 meters, h as 9 meters, and h bar 4.5 meters, again of the projected surface. E therefore is 1.5 meter. And substitute in equation of y is equal to 3 meters above the bottom of the dam. So for problem number 2, the rectangular gate in the figure is hinged at B and rests on a smooth floor at A. The horizontal component of the reaction at A therefore is 0. The gate is 5 feet wide, perpendicular to the paper or the drawing. So determine the vertical component of the reaction at A and the horizontal and vertical components of the reaction at B. So first, consider the FBD of the gate and assume directions of the forces. So estimate the location of the hydrostatic force F. So with the slope ratio same as the slope ratio of the gate, that is 3, 4, 5. Next is the reaction at point A and for point B. Therefore, we have 4 unknowns, the F, A sub V, B sub V, and B sub H. But only 3 are the required unknowns. So let us determine first the effect of water on gate A, B. F therefore is equal to the gamma times H bar times A. So from the direct formula method, where H is equal to 8 feet all over 2. So that is the equivalent vertical height of the inclined surface. Then plus the remaining 4 feet from point B towards the free liquid surface. Thus, H bar is equal to 8 feet. Substitute in equation, we have gamma of water that is 62.4 pounds per cubic foot, multiply to H bar that is 8 feet, then multiply to the actual area of the inclined surface that is base 5 feet, multiply to the total height that is 10 feet. Thus, F is equal to 24,960 pounds. Next is to determine the value of eccentricity E, where E is equal to 1 all over 12 times b times h raised to 3 all over a times y bar. For y bar, using ratio and proportion, since we have the component ratio value that is 3, 4, and 5. And this is associated to the h bar. Therefore, we have the ratio that is y bar all over h bar equal to the hypotenuse 5 over the vertical, which is 4. Therefore, y bar is equal to 10 feet. Substitute the values in equation of E, which is B as 5 feet, H as 10 feet, and y bar as 10 feet. Therefore, E is equal to 0.833 foot. Next is to eliminate temporarily the reactions at B by applying moment at point B. So the clockwise moment is equal to the counterclockwise moment. The clockwise moment is the moment due to the reaction at A, multiplied to the perpendicular lever arm that is 6 feet, equal to the counterclockwise moment due to hydrostatic force F, multiplied to the perpendicular lever arm, the combined 5 feet plus E. Rearrange and substitute F and E. The value of A sub V is equal to 24,266.667 pounds. Positive, therefore correct assumed direction, which is upward. Next, let us apply some forces of or along horizontal equal to 0. To the left is equal to the force due right. The force to the left is the unknown B sub H. And to the right is the horizontal component of F, that is F sub H. Using the component ratio that is 4 all over 5 for our H, and substitute the value of F, the value of B sub H is 19,968 pounds. Again, this is positive, therefore it is correct assumed direction, which is due left. Last is to apply the sum forces along the vertical, which is equal to 0. Downward is equal to the upward force. The downward forces are BV and FV, but transpose already FV at the other side of the equation. Then the upward force is A sub V. So using the component ratio that is 3 all over 5 for the force vertical of F, and substitute the value of F, BV is equal to 9,290.667 pounds. Again, positive, therefore, correct assumed direction, which is downward. So all forces are positive, therefore, correct assumed directions. So if the value is negative, then consider other direction and omit the negative sign. So again, for various problems, it is your discretion on what method or formula to use as long as you are comfortable of using it. So that's it for our topic, hydrostatic force for an inclined surface. Take care and God bless.